Thank you very much, Alan. Well, it's really nice to see you all. Some of you I haven't seen since this pandemic started. Well, since the pandemic started. Yeah, many of you, the European ones, well, we kind of managed to see each other somehow, but especially people from the United States, from Iran, I haven't seen in such a long time. Very nice to see you again. Thank you, Vera, for inviting me. And also apologies to those speakers of yesterday. I had serious problems arriving here, and so I didn't even make it to the afternoon talks. So, sorry. So, you know, after not seeing you for such a long time, I thought, well, perhaps we should just tell each other what we have been doing in kind of a global words. So I'm not going to talk just about one result. I'm going to talk about a series of things that have interested me in the last couple of years. And there will be some results, there will be some program. Well, so, and a part of this talk is about results joined with Wieslaw Kubis, which some of you perhaps have already seen. And the part of this talk is kind of dreams that I'm working on right now. So let's see. By the way, IRIF stands for the Institute for Research in Fundamental Computer Sciences. And well, you will see some connections with what this means. In France, this means logic and discrete mathematics, basically. But there is some logic in computer sciences that's very interesting, and perhaps I'll make some parallels with what people do in there. We'll see. So I have this project from finite to infinite, which is funding me. And it is studying the passage from properties of finite to those of infinite structures in order to get transfer of certain properties. Well, most people study this, so let me be more specific to show you what I actually mean. This could be small or big Ramsey degrees, things that Natasha will be talking about, or graph theoretic invariants, logical properties, and some algorithmics as well. Well, I'll mention some examples. And the project that I'm looking at right now is to try to develop a different view of what we mean by effective properties of structures of size Aleph1. So much of this talk will be about structures of size Aleph1. Well, of course, these are structures that we have been looking at from various points of view. And well, there will be just one new point of view, perhaps, to look at them in this way. And some of that, as I said, is joined with Wieslaw Kubis, where we look at some classes of nice structures of size Aleph1. So let me start by, well, mentioning some results of, did I skip a slide? No, okay, so it's just some results that I'm not going to talk about, but which fit into this program is a paper that I've already spoken about some years ago with Ivan Tomasic, where we use this idea of graph forms to prove, to reprove Tau's regularity lemma and get better bounds. So these graph forms are an example of how you obtain an infinite structure of the size of the continuum. A graph form is a continuous, or it's not continuous, it's a measurable function that can be seen as a limit of a sequence of graphs. And you can play with this duality between finiteness of those graphs and the continuous structure of the graph form to obtain some transfer properties. And in this context, it was about, well, something to do with regularity lemma. And we got some results that apply to classes that people study in model theory. So, and another aspect of this work is a work that I've been working on with Dana Bartoshova, Rehana Patel, and Lynn Sko. It's about big Ramsey degrees in ultra products of finite structures, where we basically showed that if you have a sequence of structures in the same signature and they come from something that has nice Ramsey degrees, then this carries to internal colorings of the ultra product. So well, that's for some other time. So just to to put this computer science perspective into this, maybe let me just say that, of course, for us in mathematics, we study infinite objects naturally, but perhaps it comes as a surprise to those who haven't thought of this before, that also computer scientists study infinite structures big time. Of course, we know about Turing machines and the automata, the infinite words, which, automata are often about finite words, but there are automata on infinite words. Our colleague Itai Niemann has done some very important work on that. And also Shella and Budevich and others, plus. People also study in computer sciences termination processes in which they connect some process with some order that's given on the states. And the idea is if you have a well quasi-order, then there will be a termination because there will be no infinite decreasing sequence. So well quasi-orders are very important in computer sciences. Something that's more new, perhaps you haven't seen this yet, is this concept of small infinite sets that's introduced by Bojanczyk in an upcoming book. It's something that is motivated by data automata, but in fact, you can think of this concept simply as countable structures that have a very simple structure of the automorphism group. And why do they study infinite objects? Well, because actually computer sciences is not about one fixed computer, but it's about networks. It's about processes that go on a number of which are dynamic, and so it is not reasonable to think of them as being bound by any finite size. So you can think of this like these people are studying what you might say is a potential infinity, as people started thinking about in Aristotle time, and maybe before. But of course, we in set theory study the actual infinity, the cardinal numbers, etc. And people say that Cantor named the infinity. And so when we were looking at traditionally into our actual infinity, we have the tendency to compare that with the actual finite and to try to carry the properties of the actual finite to the actual infinite. So, to see what applies to all countable structures, what applies to all structures of size (1). And often we find that it's difficult to carry things. So not that many things carry over from the finite to the infinite, especially to objects of size (1). So, well, here is a nice book that everybody knows, which has that exact approach of finite and infinite combinatorics, where you look at them as kind of a reflection of each other. Well, so in more recent times, people have been looking more into the process of how the infinite structure is generated. And of course, in forcing, that is one of our specialties, that's what we do. If we look at structures that are constructed by some forcing approximation, we look at how they are constructed from those approximations. So this is actually something that we do, but this is also something that people do in other subjects. Having realized that controlling all structures of a given size is often too much to ask for. So one can look at various limits of finite structures. That could be the Fraser limits that have made a lot of success in our community, or the graphones, or various versions of graphones are an example of what people call combinatorial limits. There are other ones, such as graphings. The most general one is this one called first order convergence. That's developed in Prague mostly, and also by Patrick Osona de Mentes, French mathematician who spends a lot of time in Prague. Morasses that I will mention, ultra products that everybody knows, and some other ways of thinking, including these small infinite sets that I already explained. So what kind of limits can you obtain out of the finite structures if you don't use forcing? Okay, so just instead of see what kind of limit you might obtain, well, of course, you could obtain the Aleph zero, like in the Fraser constructions. You could obtain the Aleph1, the successor, like in morasses, or you could obtain the exponential like in an ultra product. So you see our favorite problem of the continuum hypothesis can be also seen as having a reflection in the world of computer science, because this is like the P and NP problem. We have asked if these two ways of getting, if we can reduce the exponential to the successor. So now I mentioned some words like effectiveness, so I want to explain this this idea of approaching effectiveness at Aleph1. So what does it mean for us to be effective? So when you speak to a set theorist, what we mean by effective, we basically mean something which is nice or definable. So, you know, descriptive set theory. And of course, descriptive set theory starts really with CH, because it was Cantor and Bendixson who proved that CH is true for closed subsets of the reals. And of course, this gives rise to various hierarchies like F sigma sets that are also satisfy CH. And then we can have various hierarchies that we love to study, which are sort of built. So I'm writing these definitions that everybody knows, just to remind you that these hierarchies are about sets that are nicely built out of nice sets. This is the idea of what descriptive or nice means, and we can obtain many hierarchies. And these hierarchies have a connection with Turing computability. Well, there is the subject of effective descriptive set theory. We started with Kleene, developed by Moskovakis and many others. And this leads to a classification method in polar spaces, of which we have some examples that we all know. The reals, the Cantor space, but we also have some examples that are very unexpected, and people in descriptive set theory have been able to apply the methods to various contexts. Thinking here of the work of Kekris, Rosendahl, and others. So this all relies on this notion of Borel reduction. So these translations into a descriptive set theory of other objects, but the Cantor space and the Baire space rely on the notion of Borel reduction. And these are very good methods to say that the problem is unclassifiable because it's complete in some complicated enough class. Well, so this is exactly what the people do in complexity theory in computer sciences. It's also about classifying problems, difficulties of problems by comparing them to something that's known to be complete in a class. Now, how about Aleph1? So all of this is about countable. So now I'm here in a place where deep theories are discovered about descriptive set theory of 2 to the omega 1. But let us just remind ourselves what we know about Aleph1. So Aleph1 is kind of a place where everything falls apart. So that means that if you look at for big theorems of set theory and model theory, well, they tend to fail at Aleph1. So for example, the compactness theorem fails miserably for the logic in which you allow to have uncountably many quantifiers and connections. The Ramsey theorem fails. Well, we all know this by theorems that people developed, like Stevo. Well, so the analog of descriptive set theory, I say here fails, which is not to mean, this is not to say that we do not have a very beautiful theory, which is very interesting and it is very deep. But the expected translations, you know, one-to-one translations of what we know about the descriptive set theory on the countable fail at this level. So we do not have the same methods. Well, of course, the most famous failure is, I guess, the failure of the Koenig's theorem, because we have an Aronshine 3, which exists at Aleph1, but not at, doesn't exist at Aleph 0. And so we don't really have this effectiveness notion, you know, so we have some ideas of how to do it. and we have some knowledge that the methods from Zero do not really give the same level of effectiveness. Could we develop a different effectiveness? So maybe we can turn the tables and look at a different way of constructing effectiveness on this level. So that's what I've been working on. So there are two aspects on this. One is to concentrate on sets that are built nicely in some controllable way. So we can actually argue about such sets from knowing something about their approximations. So that is this idea with limits. And there is a different idea, which something that I've been developing. It's to concentrate on a different notion of effectiveness than what we get from Borel hierarchy. So if you think of Borel hierarchy as being somehow connected with Turing machines, or these other hierarchies somehow connected with processes on Turing machines, well, how could you simplify this? You could simplify this by looking at simpler models of computation. And what are simpler models of computations? Well, these are automata. So we could try to look at very definable sets, if you want, or very simple subsets of omega-1, which are connected to automata rather than to Turing machines, and see if we can develop some descriptive set theory for that. So here is an example of such an automaton that is actually, from our point of view, perhaps the first thing that we would think about, but it looks very wild when you show this to computer scientists. So what's an automaton? Usually, how does it look like? You have some partially ordered structure, and you have some alphabets, and you are allowed to go through the elements of these structures are called states, and the order is called transitions. And you have some rules how you can transit from one state to another. And as you transit, you produce a word of this alphabet by putting even though the alphabet is finite, you could produce infinite words if you have right to have infinitely many transitions. And this is known, of course. And people have looked this on various ordinal-based automata. So as I mentioned, the work of Jutta Niemann and others. But people have also looked at this on trees, but not on trees as we know them, on countable, or on trees, on the tree of the countable binary sequences, of finite binary sequences. So these are famous results of Rabin that led to some sort of decidability results, Bushi and others. Okay, so how about looking at this on and basing ourselves on the Aronshine tree? So we can have an automaton, which is, well, now you can read all this notation, but this is exactly what I described. You have the nodes of the Aronshine tree are your states, and then you can make transitions according to some rule, and you have to decide what's the rule that will let you pass the limits. And of course, you have to know what are the accepting states, like in any automata theory. So a run is a kind of a sequence that you obtain obeying these rules. So this is in symbols what I have just said. So it's a rule how to produce runs. And then you can ask various questions. So what are the type of questions that one can ask? So the first type of question that you ask is if the emptiness problem for an Aronshine tree is decidable. So this is an analog of what people have done, for example, for Bushi and Rabin automata. And let me just tell you that just going to the level of height omega +1 is not known. So this type of automata on a binary tree haven't been studied from the point of view of decidability, even on the level omega +1. So these are hard questions, and you have to make some decisions. And then you can ask about non-deterministic ones, because well, these classical automata have the property that the non-deterministic ones are equivalent to the deterministic ones, but the proofs get harder as the automaton gets more complicated. Even for the Bushi automaton, it's not trivial. And you can connect this with monadic second order logic. So, well, so this is kind of a program which in case that we get some positive answer, would indicate that Aronsheim tree automata give a good notion of effectiveness. Because once you have sets that are defined by automata, they are closed under some natural operations. And you have effectiveness because you can decide about that using this automaton. So this would be kind of a simplified descriptive set theory on omega 1. Okay, so by the way, I gave up a wrong across a wrong proof on the Marx-Tank exchange, which I thought would be amazing to would be amusing to share with you. So when I started looking at this, well, the first idea would be to reduce to binary Aronsheim trees. Okay, so you ask yourself, is there a binary Aronsheim tree? And if you think of this, this is not a completely trivial question. And it's an exercise in Kuhnen's book that somebody attempted to solve on Marx-Tank exchange. The solution is, in my opinion, wrong. Well, there are binary Aronsheim trees, such as the tree T of rho 3 that is a stable tree, but I don't know what solution Ken had in mind, actually. I don't know, maybe somebody knows and can tell me. Anyway, you can come up with interesting questions about Aronsheim trees just by studying this type of concept. And you can also think of this kind of thing as we in set theory like to give foundations to mathematics. We also give foundations to computer sciences. These days, everybody talks about the metaverse, but nobody has absolutely any definition of that. And I don't know about you people in the working in the United States, but in Europe, they put a lot of emphasis on developing this metaverse, but nobody even knows what metaverse is supposed to be. So one possible answer to this metaverse would be to have this type of automata that run at the same time as constructing something else in a different universe of set theory. So for example, rather than looking at an Aronsheim tree, you could look at a Suslin tree that you are constructing in some process like along a morass, what morass is soon. And you're constructing this morass, you're constructing the Suslin tree, which will only exist in the next universe. And you can you just need a coin reel to construct this, as we know. We can view this coin reel as something very effective given to you that is developing in time. And so at any given time, you are sitting in your universe of computation, and then at the end, you are going to pass eventually to this metaverse, to another universe. So, so this is one way of seeing that. Okay, so now let me give you some concrete results about morasses. As you can see, morasses are involved in many of these things. So what's a morass? So morass is a way to build objects of size Aleph1 using finite approximation. I'm sure that many people in the audience already know about this. Probably more the older people in the audience, because these constructions with the morasses were popular at some point, and then perhaps were somehow put in shadow by a beautiful development of constructions by coherent sequences, which construct many nice objects of size Aleph1. For my context, these morasses are more important because they are built out of finite pieces. So I'm sure that one can look at hidden sequences and see something like that there as well. But okay, this approach is very convenient for us. So for example, one result that was reproved using morasses is how to get a Suslin tree using a coin reel. These morasses were introduced by Jensen, who studied two cardinal properties in L. He showed that these morasses exist in L. They get to be very, very complicated. And basically, they are a way to build objects of size, say, kappa plus n, using approximations of size less than kappa. And people have been looking at this now in the context of forcing objects of size Aleph2 by finite approximations. Spencer Unger has been looking at that. But we are just interested in very simple, the simplest possible morass is omega-1 morass. So we take pieces which are finite and we construct an object which has size Aleph1. And moreover, we use a vastly simplified context introduced by Velleman. He introduced something called simplified morasses. And this object exists in ZFC. So let me show you what this object is. I'm going to put the slide. Looks horribly complicated. So that's why we have the blackboard. So what is it? It's kind of a Fraser limit on steroids. So, you know, in a Fraser limit, you have some partially ordered or quasi-ordered family of finite objects, and the theorem tells you that you can glue them together if between them there are some ways of gluing them together locally. So if you think of a Fraser limit, you can picture it, Fraser limit, I should say, you should picture it like this. You know, you have this Fraser limit, and inside of it, it's built out of those finite pieces, and the finite pieces have some local amalgamation properties in order to make the construction break. Now, the morass is a little bit like that, but there is more order in it. Well, at first, it looks contradictory. You have this omega-1 size object. We shall always think of objects as living ordinal omega-1. And you have countably many approximations to it, which live of finite numbers, finite ordinals. So these are theta n for n less than omega, and this omega-1 is theta omega in that notation. And the trick is you can glue them together because you are not just using any old amalgamation, but you are using amalgamations that are controlled by family of functions. So between any of those two, you have a family of functions, let's say Fmn, which satisfies some concrete properties. And you have some functions from each level to this omega-1. And now, how do you use such a thing? These functions cohere between them. So these are, you know, really nice amalgamations. And what you can do is, for example, imagine you want to construct a graph on omega-1 by gluing these finite pieces. You could put a graph structure on each one of those and then carry that graph structure through these functions, and the properties of the morass guarantee to you that you won't have any local contradictions. So if you say that these 2 points are connected, and you then say, then the images are connected, you will not have a contradiction. No other finite piece will tell you that they are not connected. So in this way, you can construct nice objects on omega-1. And with Wieslaw, we study kind of the class of objects built along such a morass. So, you know, it can be, well, let me maybe not give you all the notation because I'm running out of time, but you can just think that you have some relational language and you're constructing graphs or orders or whatever. So what did we prove? Okay. So if you fix a language and you look at the class, you fix a morass, you fix the language, you look at the class, and we want to have some properties that are common to this whole class. And the way that we construct them is, as I explained, by carrying the structure. So the first question you might ask is, well, does this class actually depend on what morass you choose? Because the morass is not unique. That would be bad news. But, well, first theorem is that it does not. So we get isomorphic objects. That is, we get a class such that every element of that class, if you fix another morass, every element of the first class has an isomorphic image in this one and vice versa. So it doesn't matter what morass you start. And then this connection with Fraser limits is something that she proved. In fact, if you look at this morass, you can see it as a model which is approximated by Fraser limits. So it's kind of Fraser limits like that. There is a club of places where we just have a Fraser limit. And we can exactly say what's the age of that Fraser limit. So, and in conclusion, this model of size omega-1 is homogeneous. So this gives you a factory of building homogeneous objects of size omega-1, which I think are of some interest in Ramsey theory. Well, I'm sure that Natasha will be talking more about that. I saw her title. And you can also construct some homogeneous graphs of size aleph-1, or we answered some open problem about the existence of a homogeneous antimetric space of size aleph-1. So what's an antimetric space? It's like a metric space, but you have in every triangle, you have the longest size, which actually has length bigger than or equal than A plus B. It's bigger is 14. And you can prove that one can prove, Wieslaw has proved that these objects cannot exist of in size C plus and bigger. But they can. The question was if one can construct one of size aleph-1. Well, yes, using this methodology. And then a Ramsey conclusion. What's the Ramsey conclusion? Well, since we have this nice connection with Fraser limits, and much is known about the Ramsey properties of Fraser limits, starting from the paper of Kekris, Pestovic, Dortwich, and then going to a whole body of research, including Natasha's research, and there's one of Dana Bartoshova and many others, okay, who work on this. We obtain, since we have this corollary that our large structure of size aleph-1 is isomorphic to the union of the Fraser limits, we obtain homogeneity, and then we can formulate various Ramsey properties, basically saying if these finite structure come from a class that has small Ramsey degrees, well, then the whole thing of size aleph-1 has big Ramsey degrees. And this is interesting because I think it's interesting because this is really going against that philosophy that nice things don't work on aleph-1. So, you know, you really don't have any Ramsey structure on all structures of size aleph-1. But if you consider these nicely built ones, you do. And then, you know, you can construct nice examples of structures using a morass and a coin reel. So the coin reel is used to somehow tell you how to construct those finite things. At every n, you use the value of the coin reel at the level n. And I don't know, people have used this. I use it to construct some space in Banach space theory. So you can construct complicated objects with this idea in mind. But so far, people have only looked at coin reels. I don't know why. It's maybe the tradition. So we're now looking also what kind of things you can obtain when you use another kind of reel, coin reel. So, you know, there is a nice concrete way to use the coin reel in these constructions, but probably there is a way to use some other kinds of reels. Well, I think I went already 3 minutes over my time, so I apologize for that, and I thank you for your attention.